Now let us go for ethers. So ethers are also the compounds which are having the heteroatom as oxygen. So general formula of the ethers is ROR, or otherwise we can also show ROR dash. In the first case, both the alkyl groups are same. We can call them as the symmetrical compounds, symmetrical ethers. In the second case, if you see, the alkyl groups are different. These are unsymmetrical ethers. Unsymmetrical ethers. And as per the IUPAC system, we have to give the names for the ethers as alkoxy, alkoxy, alkane, alkoxy, alkane. If you take for example CH3O CH3, here both the alkyl groups are same. The compound name as per IUPAC system is methoxymethane. Methoxymethane. If you take two different alkyl groups, that is for example CH3O C2H5, here this is having the less number of carbons, this have more number of carbons. So while writing the name alkoxy, alkoxy should have the less number of carbons. So here if you can take here, this is methyl plus oxy, methoxy, and this is ethane, ethane. So name of this compound is methoxyethane, methoxyethane. And you take for example another case where CH3O CH2 CH2 CH3. Here we have 3 carbons, which is the propane. Now in this propane corresponding product here, the OCH3 can be present here on first carbon, second carbon, but as per presentation that is present on the first carbon atom. That's why this is 1-methoxypropane, 1-methoxypropane. If it is present on the second carbon, this becomes 2-methoxypropane, 2-methoxypropane. Okay, and according to the IUPAC system, if it is common name, generally they are called as dialkyl ethers. Otherwise, alkyl ethers in the case of the unsymmetrical ethers. Unsymmetrical ethers. If you take for example, this is dimethyl ether, this is ethyl methyl ether, ethyl methyl ethyl. So likewise, we can give their corresponding names both in common nomenclature as well as the IUPAC system. And coming to the ethers here, if you take the corresponding oxygen, this corresponding oxygen is sp3 hybridized. So simply we can say the ethers, if you compare with water molecule, in water molecule oxygen atom is sp3 hybridized. Just replace 2 hydrogens with the corresponding alkyl groups, we can observe the ROR as the corresponding compound. So that's why if you come across ethers also angular in structure as like a water molecule, because in the case of ethers also the central oxygen atom is sp3 hybridized, sp3 hybridized. So along with that, it is having 2 bond pairs on the oxygen and also 2 lone pairs will be present. So overall, the structures of ether we come across around the oxygen atom, it is angular or V shape. Now let us see the preparation. That is the preparation of the ethers. We have various methods for the preparation of the ethers. Preparation. The first method is dehydration of alcohols. Dehydration of alcohols. If you take for example ethyl alcohol. Ethyl alcohol can give various products in presence of the concentrated sulfuric acid. The product what we got will depends on the temperature condition. If you take ethyl alcohol in presence of the concentrated sulfuric acid at about 110 degrees Celsius, at the lower temperature we will get ethyl hydrogen sulfate. Ethyl hydrogen sulfate along with water. Or if we use the temperature of 140 degrees Celsius, we'll get the product as diethyl ether with water. Or if we use the temperature of 170 degrees Celsius, 170, we'll get C2H4 along with water. So every case we can see water molecule along with different products. Simple, remember this is 110 plus 30, 140. 140 plus 30, 170. So we are keeping on increasing the temperature. So at lower temperature the alcohol reacts with sulfuric acid to give ethyl bisulfate or hydrogen sulfate. If we increase temperature to 140 degrees Celsius, we will get the product as the corresponding ether. In this case the ether is diethyl ether. If we increase further, the corresponding alcohol loses water molecule to give the corresponding alkene. In this case the alkene formed is ethylene or ethene. Ethylene or ethene. So actually we need the preparation of the ethers. So that's why alcohol under given conditions of temperature in presence of the mineral acids like sulfuric acid or the phosphoric acid H3PO4, under these conditions or under these presence of the acids, they undergo dehydration to give the corresponding products as the ethers. And very important thing here it is, the alcohol what we are using here, it should be generally primary alcohol. If we can use secondary or tertiary. Whenever we use the secondary or tertiary, the reaction is in dehydration, but the final product here we may expect ether, but we'll always get the corresponding alkene. The corresponding alkene is the major product. That's why here the elimination predominates over the formation of the corresponding ether always. That's why in this case we have to use generally the alcohol as the primary alcohol, not the secondary or tertiary. Because if we use secondary or tertiary, we will get finally the product as the alkene, which will form the alkene by the elimination reaction. Now we can also use other methods for the preparation of the ethers. That is Williamson synthesis. Williamson synthesis. Williamson's synthesis. So in this synthesis, generally the alkyl halides will react with sodium alkoxide. Sodium alkoxide in presence of the dry ether or the reagent. Here we will get the ROR dash. ROR dash. So here we will get the corresponding product as the ether. This reaction is called as Williamson synthesis. So generally the corresponding alkoxide what we are using must be can be primary or secondary or tertiary. But coming to the alkyl halide, this must be primary. If you take for example methyl halide CH3X and you take the CH3ONA, sodium methoxide. Sodium methoxide will get the product as CH3OCH3. Methoxymethane. Methoxymethane. Or you take C2H5X plus CH3ONA. The product is C2H5OCH3. This we can observe the formation of the corresponding ethers. Here the ether formation, we are taking alkyl halide as well as sodium alkoxide. The alkoxide what we are using can also be like primary or secondary or tertiary. But alkyl halide must be the primary only. If you take for example, I am taking the corresponding alkoxide like this. Alkoxide and CH3X methyl halide, which is the primary one, will get the product as like this. But if you use the corresponding alkyl halide like this, which is a tertiary alkyl halide, I am using here, and the corresponding alkoxide like this, which is sodium methoxide. Here also if you come across, we may expect this product, but we won't get this product. The final product what we get here, it is this is the product what we get here. And if you see both the case, but here if we are taking the primary alkyl halide, but here we are taking the tertiary alkyl halide, and the corresponding sodium alkoxide we are using. And why the product here it is this one, and why the product is here it is eliminated product. The reason we can explain by considering the corresponding sodium alkoxide. The sodium alkoxide, if you take here, this RONA will give RO minus and Na plus. Now this RO minus generally can act as a nucleophile, and also remember it can also act as the base. So whenever it acts as a base, it have the ability to remove the hydrogens, to eliminate the hydrogens. So that's why whenever it acts as a base, it will generally prefers to give the final product of this kind. That's why we can expect the eliminated product, and this will be the major product in presence of the corresponding alkyl halides, which are tertiary alkyl halides, because in the reaction if you see here, this will be removed as halide. Now we can get here the tertiary carbocation, and we are aware that the tertiary carbocation is highly stable. That's why whenever we use tertiary alkyl halides, the final product is the corresponding alkene. This is a very, very important point that one has to remember in the preparation of the corresponding ethers. And what we can get? We get either ether or we can get the eliminated product. Okay. And also if you come across about the alcohols, we have discussed the we can prepare the alcohols or we can use the alcohols to get the ethers. In such a case, we have to use only the corresponding primary alcohols, but not the secondary and tertiary alcohols. Just now we have discussed. If you use secondary or tertiary alcohols, instead of getting the ethers, we are getting the corresponding alkenes. These are the major methods of the preparation of the corresponding ethers. Now let us go for the properties. Properties of ethers. In the ethers we have ROR. So this bond and this bond which have carbon oxygen. So these bonds are polar bonds. So because of this, generally they have ability to dissolve in water like polar solvents. But the solubility of this corresponding ethers in water is a little bit less when compared with the corresponding alcohols, because alcohols have the ability to form the intermolecular hydrogen bonding. But coming to ethers, only the lower ethers have the ability to form the corresponding hydrogen bonding with water. That's why they are miscible, especially in the lower ethers. But coming to higher ethers, because of the hydrophobic like alkyl group, they do not participate in hydrogen bonding formation. That's why the solubility is less. At the same time, ethers are more volatile when compared to the corresponding alcohols, because in the case of alcohols we can observe hydrogen bonding which leads to give association, but in the case of ethers there is no such kind of association with respect to the hydrogen bonding. That's why ethers are more volatile. That's why they will show or experience, they will show the lesser values of the boiling point. So volatile nature is more in the case of the ethers. Now let us go for the chemical reactivity. The chemical reactivity of the ethers. Here in the chemical reactivity of these ethers we come across, here whenever we come across about the reactivity, it is difficult to break the bond which is present between carbon atom and oxygen atom of the ethers. But under drastic conditions, that means by providing the required conditions, we can break the bond between oxygen atom and carbon which is present in the ethers. If you take for example the reaction with the hydrogen halides, so especially the hydrogen halide will be HBr and HI. The reason is, among the hydrogen halides like HF, HCl, HBr and HI, so among all these two are more acidic in nature and compared with HF and HCl. That's why these will predominantly react with the corresponding ether to give the corresponding products. If you take for example ether, I am taking it as ROR. If it reacts with the hydrogen iodide HI, so this will give one as alcohol, other one as alkyl iodide or iodoalkane. In this reaction if we come across, here H plus and I minus will be formed. H plus and I minus will be formed, and I minus is a good nucleophile because having the I minus means it having the electron pair that can be given to the corresponding electron pair acceptors. So whenever I minus will attack, it will always attack the corresponding compound or alkyl group which is less substituted. At the same time, this is a symmetrical ether. You can also take unsymmetrical ether, ROR dash. So this also will combine with HI to give ROH and R dash I. So here this should have the corresponding substituents are less, because I is the bigger one. It will always try to attack the alkyl group which is having the less number of the substituents. Okay, and here if you come across about the mechanism of the reaction, generally this is ROR. If you take HI, hydrogen iodide, this HI will first, the proton will attack on the corresponding oxygen atom, so that we will get RORH along with I minus plus, because oxygen have the 3 bonds. Okay, and finally this will releases the corresponding R plus. That R plus will react with I minus to give the corresponding product as ROH and RI. This is how I can expect the corresponding products. Okay, and as I told you here, we will come across about the ethers, if I take here for example, this is the ether, the reaction is with the HI. As I told you, the I minus will attack the alkyl group which is having less number of substituents. But coming to this case here, the product what we get here, it is tertiary alkyl iodide along with CH3OH. The reason for this is, if you eliminate this like this, we will get the carbocation, which is tertiary carbocation. Where the tertiary carbocation is highly stable. That's why we will get this product. But if it is tertiary one, as I told you, always the I minus will attack the corresponding alkyl which is having less number of substituents. And apart from that, you take the similar kind of reaction with ether which is having the aromatic ring. You take for example anisole. Anisole is methoxybenzene. Now if you take this here, among these two, this is having less number of carbons. This is having the more number of carbons along with the corresponding conjugate system which is aromatic system. Now if you take this particular bond which is present between oxygen and carbon of CH3 and oxygen and carbon of the benzene ring, and as we are aware that this carbon is sp2 carbon, this carbon is sp3 carbon. Now the electron pair which is present here is delocalized with this benzene ring. So because of this reason, this carbon oxygen bond, if you come across, it will have double bond character. That's why if you compare the bond strength of this OC bond as well as this OC bond, which is stronger, means this is stronger. That's why this bond cleavage is difficult, but this bond cleavage is easy. That's why if you come across the reaction between this anisole and HI, so this bond is cleaved. That's why I'll get the product as OH and CH3I. And observe always these things. This is about a reaction with the hydrogen halides. Now this, if you come across about especially the phenol systems or the corresponding ethers which have the anisole, in the case of anisole we have the oxygen attached to the sp2 carbon atom of the benzene ring. Definitely this will give various resonance structures where we can observe the negative charge at the ortho as well as para positions. That's why these aromatic ethers will undergo generally electrophilic substitution reactions. Now let us see the electrophilic substitution reactions given by the anisole. Electrophilic substitution reactions. Electrophilic substitution reaction, that is, this is the anisole. So this on halogenation. Reaction with halogen in presence of anhydrous AlCl3, which is Lewis acid. We will get the product as ortho and the para substituted products. Ortho and para substituted products. So among these, the para product is the major. This is the minor product. This is halogenation. It also undergoes the Friedel-Crafts reactions also. Friedel-Crafts reaction, Friedel-Crafts alkylation, Friedel-Crafts acylation, like that. So here Friedel-Crafts reaction is given by the corresponding ether. If you take Friedel-Crafts alkylation, you take methyl halide in presence of the Lewis acid, which is anhydrous AlCl3, Lewis acid. So the final product here it is ortho as well as para substituted product. This is ortho product, other one is the para product. Again, the para is the major, this is the minor product. This is Friedel-Crafts alkylation. You take Friedel-Crafts acylation. This also you take CH3COCl, which is acetyl chloride, which is again this is the corresponding ether, which is anisole, reacts with acetyl chloride in presence of Lewis acid, anhydrous AlCl3, the products as ortho as well as para products. This is ortho, the other product is the para product. Again, the para product is the major product. Minor and major products. This is Friedel-Crafts acylation. And also these can undergo the nitration also. If you take the nitration reaction, this is anisole, take the nitration mixture, which is concentrated HNO3 and the concentrated sulfuric acid H2SO4. This will give the para and ortho substituted products NO2. This is ortho OCH3 NO2. So para is again the major product, ortho is the minor products. This is about the various electrophilic substitution reactions which are given by corresponding ether.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.